I'll talk about accessing data while preserving privacy. This joint work with George Kilaris, George Colliers, and Adam O'Neill. And an apology or an excuse. This is new stuff, and even this morning I was thinking whether I should present this or another work. So you will see. So they are still missing stuff here, but I thought that like in this friendly environment I can allow myself to present this work. We're in the process of writing it down. So I'll talk about outsourced database systems. And think about your bank. The bank has clients, and it collects information about clients. These are records, client records. And it's not enough just to collect that information. It collects, puts that in a database in a way that is easy to access. So there are these attributes. I'll call that indexing information, like the name, zip code, gender, age, and so on. And then after collecting all that information, the bank could now try to retrieve some of this information. For instance, the bank may need the records of clients that are named Gina. I'll call that a point query. Or clients whose age is between 32 and 52. And I'll call that a range query. And the clients with the sex being male. And I'll call that a one-way attribute query. And you could also combine attributes like the sex is male and married and not married. And that would be a two-way attribute query, and so on and so forth. Okay, and you can think about a rich language of queries that the bank may want to use in order to query this database, to retrieve the relevant records at every time, and so on. But banks like to make money and not to work with databases, so the bank could think, I'm too tired to do this, it's too boring, I don't want to work with the data myself, and hence we have these services in the cloud, and the cloud suggests if you delegate your data to me, you don't have to do the boring stuff, you can just make money, and that's great. But the bank is worried, I can't just give my data to the cloud. Maybe I don't trust the cloud with my customers' data. Okay? And being cryptographers, we can say, oh, we can use crypto. We have a lot of schemes to delegate this kind of computation and so on. We have solutions for doing that. Great. So before delegating the information to the cloud, the bank thinks to itself, this sounds like a great idea. We'll use very strong cryptography or cryptographic solutions in this delegation. But is this efficient enough? Will I get my answers in time, or will I have to wait a lot for answers to my queries? And even if I use this crypto, is this secure? Okay? And there are solutions out there. For instance, in the crypto community, we have secure function evaluation, ORAM, FHE that we can use, PIR, searchable encryption if we're interested in specific kinds of queries, and so on and so forth. But these are considered mostly not yet efficient enough. And hence, people came up with ideas to implement systems that are both secure and practical. Okay? And these use relaxed notions of encryption like deterministic encryption or order-preserving encryption in order to facilitate an efficient way of querying the database. Okay? And this use of deterministic and order-preserving encryption allows us to use indexing and query the data while maintaining reasonable security. Examples are CryptDB and Cypherbase, but there are some other examples recently. But unfortunately, there are also attacks published on these schemes. Like one recent attack is by Navid Kamara and Wright. It was discussed in many places. These attacks are implementation specific, they are data specific. And overall, we could say that the security and privacy of these schemes is not well understood. So in this talk, I want to suggest that we can have an implementation-independent exploration of this question to learn about the inherent privacy efficiency trade-offs in these schemes. This is what I'll try to begin today. So for this talk, I will present some basic models and then discuss what are their fundamental leakage channels. And there are going to be two kinds of leakage channels that I'll consider. One is the access pattern, like if the server can watch exactly which records are returned in each query, although maybe the server would not exactly know that this is Moni's record and this is Adam's record. And maybe even the server would not really know what the query is. Okay? Can we use this kind of leakage to learn about the data? And this seems to be, like, I think intuitively for all of us, like quite a rich source of information to be used in attack. And the second channel is the communication volume. It's inevitable that at least the volume of the communication between the bank and the server would be visible to the server. Okay, so if we just watch that, does that leak information? It seems like rather a harmless leakage channel. Okay, and we'll consider reconstruction attacks. First, we'll look at optimally efficient database systems. And in a sense, all the constructions that exist today are optimally efficient. I will define that. And at the end of the talk, I will suggest how to combine differential privacy in order to get, with some cryptographic tools, in order to get what we call differentially private storage. And here again, we'll consider two models. One is like the atomic storage model. This is where the access pattern is visible to the attacker, and the more general model where we combine ORAM and sanitization techniques from differential privacy to achieve this kind of security. Okay? And caveat is I will only consider the case of static databases, so without insertions and deletions. We know how to deal with insertions in some cases. Deletions seem to be more challenging. And furthermore, I will only consider the question of the secrecy of the indexing. Records themselves can be encrypted using very good encryptions, like semantically secure encryption. So I will not be worried about data leaked from the records, but I would be worried about data that is leaked about the indexing. Okay. So let me present the first model. We call it the atomic storage model, although I think now that maybe we should rename it. And in this model, there are two stages. First, what's that? What's the question? In this stage, first there's a setup where the bank sets up the server's memory. And in the setup, the bank could choose some secret key, maybe, and use this key to encrypt the records, okay, and create some auxiliary data structure, hopefully also encrypted, and these are sent to the server. Okay. Now, when a query happens, when the bank wants to query the data set, so this is the query queue. It uses the key to encrypt the query in some sense and sends the query to the server. And now the server can combine this auxiliary information in the data structure with the query in order to learn which records should be returned. And these are returned to the bank, to the client. And using his key, the bank can decipher this and learn the content of the record. So it's a very simple model. And then the second query occurs now. And again, the bank encrypts it, sends it to the server. The server can tell, now it's this record that has to be returned. And again, okay. But note that what happened is that this record was returned in both cases, and the server could tell that this happened. So the access pattern is being leaked here, but not necessarily the query itself. So in the atomic storage model, we leak the access pattern, which means that the server always learns the number of returned records. And if the same record is returned on two queries, then the server learns that this happened. I should note that in general, in the schemes that I mentioned, a lot more information is being leaked. For instance, the content of the data structure that is sent along with the encrypted records could also be revealing. Some information about the query could also be leaked, and so on and so forth. But for the analysis to understand what is the fundamental kind of leakage that must happen here, I'm ignoring this extra leakage, and I'm only focusing on the access pattern. Now, I'll call a system optimally efficient if it does not waste communication and storage, in the sense that there's no increase in the number of stored records, no duplications, no fake records, and so on. And there's no increase in the number of returned records per query. And the reason to look at this maybe naive setting of optimally efficient systems is that all the currently existing systems are optimally efficient and work in this atomic storage model.
So why do you put efficient in quote unquote? They're efficient.
Yeah.
Not efficient.
What's that?
The problem with the current system is not efficiency.
Yeah, maybe we can get back to this later on. But more generally, we could think about systems that store duplicates and fake records, and where the number of returned records is inflated. We always have to return all the records that are requested by a query, but we could return a little more. Okay? So I want to begin with an exact reconstruction attack for optimally efficient systems in the atomic model, so where we see the access pattern. And the reason for looking at reconstruction attacks is that they proved useful in a different area in analyzing privacy. It's a tool for understanding the limitation of this trade-off. And the logic is that even if we have a weak privacy requirement, or we don't really understand yet what we're interested to get, it is clear that if somebody can easily reconstruct all the data, all the secret data, that this is not good. This is not good enough. Okay? And I'll focus on range queries, where the index is an element of a finite domain, values 1 to t, and the query is an interval. And the answer to this query is all the records would index within this interval, A to B. Okay? And also to demonstrate that there is a privacy or security problem, I want to consider a rather weak adversary. Okay? This adversary is going to be oblivious of the queries that are sent. It does not control the data. It cannot choose queries. It will only know the underlying distribution on queries. Okay? And we'll assume that this distribution is uniform. This distribution is uniform. Okay? Again, a more realistic adversary would probably have some influence on the data, may be able to choose some of the queries, may be able to learn some of the query answers explicitly, But I do want to speak about a rather weak adversary that does not have all this kind of access to the data. Okay. And because of symmetry, I won't be able to exactly reconstruct. The reconstruction is going to be up to 2 candidates because we can get like a reflection of the interval 1 to t. So on the left, on the bottom left, you have the data set itself, only for you to see, but the adversary does not see it. Okay? And here we have the adversary. This is the server, with the records that were sent to it, and they are stored on the server, like in some order, in an unordered fashion, okay? And now we'd like to perform our attack in 2 steps. In the first step, we'll recover the order between these records. This may not be that harmful because, like, for instance, if there's only 1 record per at most 1 record per domain element, it's clear that there is some order between them, and recovering that n order exists is not that interesting. But this is just going to be a first step in an attack where eventually we also recover the values. So remember that we're assuming that cores are chosen uniformly at random. Just a coupon collector argument shows us that, like, after about t squared log t queries, each query was issued at least once. Yes, Anand.
The index and the range queries are random.
Sorry?
Both the index, so the index queries are uniform 1 to t. So kind of the previous slide, except it's just the model for the.
There were point queries and range queries.
Okay, so the point queries are just uniform 1 to t.
Yeah, but now I'm assuming range queries.
Only range queries.
Only range
Okay,
queries.
so then you know the range, you know the original range of the data.
You know the original range of the data, you know the number of records, but you don't know anything else. Okay, other questions about them all? Thanks. So after seeing all these queries, there's a lot of structure that we can learn, and we can watch this structure in order to recover the order between them. So we begin with a set of all records, and we look for the query that is a subset of this set, the maximal subset of this set. So it leaves out a few records, and all these records must be in the same position, either to the left or to the right, okay, to the extreme left or to the extreme right. Let's say we put it to the left in this case, and then we continue. We look for the next maximal subset. In this case, it's these 3 records. You can recover that from the data there. And we now need to decide where to put a C2 to the left or to the right. We put it to the right because there's no query that contains only C2 and C5. Okay? So we know that they are not adjacent. We put it to the right. We continue with a sub. The largest subset that we get here, we take out C3. We have to decide whether to put it to the left or to the right. But there's no query where C3 and C2 are together, alone. So we know that it has to be to the left in this case. And then in every query, C1 and C4 appear together. We decide to put it to the left, and we get the ordering of the records. So this is extremely simple.
No, I didn't catch it. So what,
Okay.
So each time you take, so how do you decide when to
So we at the stage where we issued all possible queries. Okay, so we've seen all possible subsets here. And let's begin again with the first one. So I'm looking for the largest subset.
So first of all, there will be a query that contains all subsets.
There's a query that contains all of them. That's not informative for me. Okay, and then I'm looking at the largest subset of this query. One of them. And then what happens with this largest subset is that it left out either the rightmost or the leftmost element. In this case, it left out C5. I don't know whether it's rightmost or leftmost. I just arbitrarily decide to put it to the left. Okay? And then I'm looking at the maximal subset of what is left, and in this case is this subset. There could be also another choice here, I think. And so I'm getting that C2 is either adjacent to C5 here or here to the right. I need to make a decision. Making a decision is just examining whether there is a query where C2 and C5 appear together. If not, I know that they are not adjacent.
Appear together without
only them. We've seen all possible queries, yeah. Okay? So in this case, I don't see the query that contains both C5 and C2 and nothing else. So I know that I should put it on the other side and so on and so forth. Okay? So we recovered the order of the records. Now we want to actually learn their position. Now, there is an easy case if the index set is, if the records are dense in the index set. For instance, if at each point there's at least one record, then the order reveals everything that needs to be revealed, and we're done after just issuing t squared log t queries. And otherwise, we can try to estimate these quantities, which you can show uniquely identify the location, in this case, of C1, and you can generalize this. And in order to compute this ratio accurately enough, you need something like, this should be t to the fourth query. That suffices for computing this, and we can also show a lower bound that in the worst case this is needed. And once you have this information, we can recover exactly the position of all the records. So we get an exact reconstruction with high probability by watching this by watching the access pattern. Okay? Yeah.
The assumption that the queries are uniform isn't by that reasonable?
It's because we made the assumption. Yeah, it's reasonable because it's a good point, I think, to start with. Certainly something we would be happy to relax. One interesting question is whether you can begin by, in a sense, trying to learn the underlying distribution, and then if it's rich enough, if there's enough entropy there, try to carry out such an attack. Okay? Yeah?
It would make, like, if it was sort of a skew distribution, you knew it, non-uniform, would it make the attack easier likely or harder?
I don't know. I don't know. It's a very good question. Like certainly something that needs to be explored. What distributions are good for this attack? Yeah. Okay. Other questions?
Can you go back one slide? 2 slides. Sorry, one more slide. Yeah. Sorry.
What's that?
Okay, I was just trying to fit together the pieces properly, but it's okay. I'll ask you.
Okay, good. So the access pattern leaks a lot of information. I think it's not that surprising. Like being cryptographers, seeing so much information about the data, it's not that surprising that we can recover everything. The attacks are efficient in the domain size. There's a question what happens when the domain size is large, and I believe that there would attacks that approximate the points should still be feasible, but this is something that we didn't do yet. And this is the complexity we get. But what if the access pattern is hidden? Okay? And as we said, we have crypto solutions for hiding the access pattern. Okay? The communication volume would still be visible because there's a number of records that you need to return. And optimal efficiency means that if the records are big enough, then they dominate the communication. Like there may be a little more overhead. But knowing the size of the record and the communication, you can determine exactly how many records are being returned. Okay? This is achieved by a lot of the crypto-based solutions and seems to be harmless. Or is it? Okay. And the answer is that it's probably not. Not. Okay? So the next result I want to show is an exact reconstruction for optimally efficient systems in the general model where you only see the communication volume. Okay? And I'm going to make an assumption that will make my life easier. I believe we can get around it, but I'm not 100% sure yet. And this assumption is that there is at most one record per index point. Okay? But there's still this still allows for like a lot of entropy in the data set. So I want to recover the positions of the records in the data set. And in order to do that, assume we've seen enough queries. Order of t to the fourth queries are sufficient and the worst case needed. That we can estimate out of the t choose 2 queries how many queries returned I records. Okay, let me just to make this concrete, do it for this case on the left. If you look at this query, the red interval there, if this is the query, then you return 4 records. Okay, and also if this is the query, you return 4 records, and also for this query, 4 records. Oh, sorry. So for these 2 queries, 4 records are returned, so I put here a count of 2. Okay. Now, how many queries return 3 records? This query, this query, this query, and this query. All of them return 3 records. I have 4 queries like that, and so on. I won't do the count for the case of 2 records and a single record. Okay. You could also count how many queries return 0 records, but knowing the sum is t choose 2, this doesn't give us any more information. Okay, Adam, you seem confused, or is it fine?
Yeah.
Okay, what confuses you?
I got lost in something.
Okay, so again, assume we issued all t choose 2 queries. Okay, how many of these queries return this number of records, 4 records? These are the queries that contain the interval 20,000 to 80,000 in this case, and there are 2 queries like that. Okay, so this is why the count here is 2 and so on. And we assume that we took enough queries in order to estimate these counts well enough.
Okay, so again, is it like you're assuming that all possible queries are asked?
Queries are being asked uniformly at random. But now I'm asking, out of these t choose 2 queries, how many queries returned?
What does uniformly at random mean? Meaning like A is chosen random?
Of the t choose 2, yeah. Yeah.
Of the t choose 2 possible ones, I'm selecting uniformly.
Uniformly at random. You repeat that t to the 4th times. Okay, I'm telling you that this allows me to estimate out of the t choose 2 queries how many return an answer that contains 4 records.
The assumption is that that the communication pattern tells me exactly the number of records.
Exactly, yeah, but nothing else.
Say for like an ORAM scheme.
For ORAM, exactly. FHE, ORAM, you will learn the communication volume.
Unless you go out of your way to hide it.
Exactly. Yeah. Okay. So, given this information, we can now recover the position. Let's define this interval. So what I added here, you see I added this like virtual red points, one to the right of the range and one to the left. And I'm defining these variables, which are the distances between points. This is actually what I'm trying to recover here, okay? And note that the number of queries on which I'm returning the max number of records only depend of these intervals R2 and R4. It's actually R2 times R4, R0 times R4, actually. I need to put my glasses. Yeah, R0 times R4. The leftmost times the rightmost, because this is how much you have choices here for the endpoint and choices there for the leftmost endpoint. And similarly, if you're asking how many queries return 3 records, it's that expression, okay? And in general, you're getting this collection of equalities, okay? Now, we don't know if the solution to this system is unique. We believe it is, but we don't know how to prove it. And we don't even know whether it can be computed efficiently. But we have a heuristic. So we just tried a DFS search for a solution, which means that at each level of the DFS search, we set values to 2 variables, okay? Okay. And these are integer solutions, so we need to look at like factorization of the numbers and figure out the possible solutions. And after you went to depth, n over 2, you've set values to all the variables, so the depth is never above that, and then you can check whether this is a valid solution. I believe that what happens is that in many cases this tree terminates really early, or the arity, or the branching of the tree becomes 1, and this is why in our experiments, in our experiments, this actually manages to compute a solution, like if the domain size is about 1,000, it takes about 10 seconds. From our experiments, it's always the correct reconstruction.
You shouldn't have any new solution because of the symmetry.
Up to symmetry, yeah.
And so it's not even clear, you don't care about efficiency of information theoretically, it's sort of possible.
Yeah, I don't know. I believe it should be, but yeah, I don't know.
It seems clear as you're learning a lot, right? Whatever
you're learning a lot, yeah. But whether you're always getting an exact reconstruction is a question. Yeah. Okay, so let me summarize so far. How much time do I have, Adam?
you have
5. Ooh. Yeah. Let me summarize that. This far, we see that optimal efficiency leads to reconstruction attacks, even with a weak adversary. And I am repeating that a more realistic adversarial model would allow the adversary to select some of the queries, select some of the data points, and so on. 15?
Yeah, no,
Oh. That's only a factor 3 approximation. Yeah. It's a small factor. Okay. So a more realistic adversary will be able to do all this. And it leaves us with a question whether we can achieve reasonable privacy with these systems, and certainly we'll have to relax our assumption of efficiency. So it shouldn't be optimal efficiency. Okay. And we are trying to answer, we'll try to answer this in the positive by introducing differentially private storage. It will give differential privacy at the record level, and it will allow us to deal with strong adversaries that can choose the data and can choose which queries are being asked and see the answers to these queries. Okay. So how are we going to do it? In the general model, like if we don't restrict, if we don't insist in this model where you can see the access pattern, we can hide everything except for the communication. So we will inflate the communication. This will be our way of adding noise in order to achieve differential privacy. In this atomic model where you see the access pattern, we'll introduce multiple copies of the same record, we'll introduce fake records, and this hopefully will allow us to achieve differential privacy. Okay, so I'm just putting the definition that Adam spoke about for 3 hours yesterday. And the only property I will need is post-processing, which means that if we compute with differential privacy and then perform a computation over the outcome without looking at the data again, then what we get is differentially private. Okay. And I will need a few more facts from Adam's 6th hour of the tutorial. And I'll just mention them briefly shortly. Okay, but Adam did speak about data sanitization. I want to reiterate this. It's like beginning from the work of Blum, Liggett, and Roth. Suppose we have a collection of statistical queries. Sanitization takes a data set. In this case, it's going to be our index information for the records. And then with a differentially private mechanism, transform it into a data structure so that you could think about issuing queries from this collection on the data set or evaluating them given the data structure. And the answers would be approximately similar, like within an additive difference of alpha. And we're required that this will happen for all the queries in our collection. Okay? Or it will be sometimes more convenient for me to assume that this difference is one-sided. So this evaluation based on the data structure is always an upper bound to the real value, and the difference is at most alpha. Okay? And moving from here to there, you lose a factor of 2. So I don't care about the factor of 2. And BLR showed that, in general, alpha depends on the fifth dimension of a queue, the collection of queries, the size of the domain, and the number of elements we have in the data set. This is n to the 2/3. Okay? So that's in general, but we have, for specific query classes, we have a little more efficient solutions. For instance, for point queries, under pure differential privacy, we can do it with alpha logarithmic in the domain size. With approximate differential privacy, we can do it with alpha that is a constant. I'm ignoring the dependency on epsilon and delta. For range queries, again, this can be done in logarithmic in the domain size, or with approximate differential privacy with this ridiculous function of the domain size. For one-way attribute queries, we can do it like if we have k queries, alpha can be something like root k with approximate differential privacy. Okay, so that's a supplement from Adam's 6th hour. And let me begin with a generic construction for differentially private storage. And it's a simple idea. We combine sanitization from differential privacy with ORAM in order to achieve the security. The setup is that first we compute a sanitization of our index set. Okay, this creates a data structure which preserves differential privacy, so we can give it to the server in the clear. We don't have to hide it. Okay, and the server can consult it when answering queries. Okay, so this is stored on the server. We could also store a copy at the bank, and then we use ORAM to store the records. Yes, Adam.
When you're sanitizing records with differential privacy, can you ensure, this shouldn't be a big deal, but you can ensure that you're always overestimating
This is what I said, yeah.
the query, right? That's okay.
Yeah. You remember I had this
Just said that. Somehow I'm
here.
almost with you.
Okay.
So you could just store like the n-squared numbers for all the possible range queries, right? Like.
Yeah, that could be your data
Data
structure.
structure is more
Yeah.
the same,
You could store all the n-squared numbers. Yeah. You can actually store a lot less than that. Yeah.
That's the point of the data structure. Right?
Yeah. Where was I? Okay, and so this isn't the setup. We just use the ORAM to store the records, maybe with some supporting indexing information so that we can later retrieve records. And we also store a sanitized indexing set on the server. And then to answer a query, we first evaluate an estimate of the number of queries that need to be returned. Okay. Remember, this is always an upper bound, so we'll have enough room for sending the real records that need to be sent, and plus a few maybe copies or dummy records. And this is what we do through the ORAM. We use the ORAM to retrieve this number of records. This includes all those that are interesting for the query and a few more. But this kind of noise makes sure that the communication volume does not leak information beyond what we allow it. So we preserve differential privacy. Okay, so this is very simple. And in terms of efficiency, we are getting optimally efficient storage. We don't need to save multiple copies of records. And we're getting the communication overhead that depends on this accuracy that we get from this for the sanitizer. Okay, is that clear?
What about the secrecy?
What's that?
What about the secrecy?
And we're getting the secrecy from the ORAM.
No, but you still have the size up to some, you still have the equations up to some node.
Yeah, but whatever you do now is post-processing because you are seeing the outcome of the sanitizer.
I'm not sure that
You get
Yeah.
epsilon,
Yeah.
you get epsilon notion of
Yeah.
epsilon differential privacy.
Record level epsilon differential
Yeah.
privacy, right? So all it protects against is the insertion or removal or change.
Yeah. Whatever differential privacy protects against. Yeah. If differential privacy is sufficient for your data, then this is what you're getting. Yeah. It's not that you are hiding any possible structure of, like, for instance, you could learn that there are more records in the low end of the range than in the higher end of the range. Okay. Okay. Now, you could also ask whether we can do something similar in the atomic model. Okay. And there is one reason to do that is that it will probably be more efficient than the ORAM solution. And the answer is that in some cases we can. For instance, for interval queries, what we can compute with differential privacy is something like this. If this is our range from 1 to t, we know how to compute with differential privacy, and the inputs are points here. Maybe here I have 2 records, and here I have one record and so on. What we know how to compute with differential privacy is an estimate of the cumulative number of records as we go from 1 to t. Okay, this is like a sanitization of the threshold queries. So we can compute with differential privacy an estimate of that. That will always be, as we said, an upper bound. Okay, and we'll have some distance alpha here. And based on this, we can now split the range so as to buckets, each of them containing about alpha records, maybe 100 alpha records. Okay. So in each of these buckets that we created, they are not equal sized in terms of their length, but they are about equally sized in terms of the real number of records that appear there. Like there's something between 99 times alpha to 100 alpha records in each of the bins. Okay, so this is what is drawn here. And now to answer a query, we retrieve, so what we store on the server now is a collection of records per each of these buckets, okay? The records that fall in, the real records that fall in these buckets, remember they are encrypted, so they look like random records, plus some fake records, some dummy records. How many dummy records? At most this difference that we get here, this alpha, okay? So this is what we store in each of, for each of these buckets, we give the server a collection of encrypted files. And when we have a query, the query is an interval, maybe like this, then the server returns all the files that fall into buckets that intersect the query. Okay? And then this very simple solution gives a constant inflation in the storage and a constant multiplicative inflation in the communication and an additive order of alpha inflation in the communication. So it may be that the query asks for, there are 0 real records that need to be returned, but we still return something like alpha records. Okay? But at least it gives some, like an efficient solution. It's very simple. But you could ask whether you could do it for other kinds of queries. And this is where I'll end. We also examined what happens with one-way attribute queries. And now there is a very trivial solution. For each of the k or 2k possible queries you asked, send the server a collection of records. But this means that we duplicate each record k times, plus some dummy records, okay? So we get a big inflation in memory. And the question is whether we can do something that is more efficient.
Sorry, what's the trivial solution?
So the trivial solution is that for every possible query, I store the record, I store at the server all the records that need to be returned with that query. Okay? So a query could be now duplicated k times. A record could be now duplicated k times because it will be returned in k different queries. Okay? Like for instance, these are attribute queries. So a record could be.
I'm confused what you're trying to hide here. So you're trying to. What does this protect against? The solution that you're just describing.
Again, I'm giving differential privacy at the record level in the following way. For each.
First, you're going to sanitize.
I'm sanitizing the queries, and for each query, so for each query, I know now how many records I need to return. I send the record, all these records to the server. I store all these records on the server for that query, and then again for the second query and so on. So what you get is that each record is going to be.
Using ORAM, you wouldn't need
copies. If I'm using ORAM, I'm only storing one copy of a record. Yeah. So there's like. Then you have the overhead of the ORAM, which is not probably, it will not grow with K.
It'll
Yeah.
depend on the security parameters.
Yeah, exactly. But it will not grow in K.
Is there a low bound?
Ask Moni. But there is a lower bound here, and unfortunately, every atomic differentially private storage for one-way attribute will require this inflation, this blow up in the storage. Okay, so this is, do you have a minus sign also? So this is one of the reasons why we moved to the solution with the ORAM, because we're not getting, in general, we're not getting efficient solutions in the storage model. Although there are a lot of interesting questions here. For instance, what if we relax this atomic storage model where to something, is there a possibility of relaxation so that we avoid the lower bound? For instance, if you allow combinations of records, things like that. What happens in the case of two-way attribute queries? Again, the trivial solution holds, but we don't have a matching lower bound. So it would be interesting to resolve that question, whether the inflation in memory is a factor k or factor k squared, and so on. So let me summarize in the -1 minutes I have. I claim we need a rigorous analysis of the inherent security privacy versus efficiency trade-offs for these systems that we don't have now. Optimal efficiency seems to be very bad. It leaks a lot of information. Unfortunately, all the systems that are constructed so far are optimally efficient. And we suggest differentially private storage. We can always do that combining sanitization with ORAM. And in some cases, we can also do it in the atomic model. And I think, and part of this work, George Kilaris, like the postdoc that worked with us, also implemented some of these attacks to see if they are really feasible. As I reported, like 10 seconds for recovering the order in the case of communication leakage. Also implemented the work with the ORAM. And we'll report about that in the paper that we're writing. This will. Thank you.